In this video, we will learn about finding the partial fraction decomposition for a function or expression, which means we will rewrite a certain function or expression as a sum of rational expressions. We will reference 4 cases to help us with the solution process. In case 1, the denominator would comprise distinct, non-repeated linear factors of the form ax plus b, such as the quantity 5x plus 4. In case 2, the denominator would comprise one or more repeated linear factors of the form ax plus b to the m power, where m is greater than or equal to 2, such as the quantity x plus 1 cubed. In case 3, the denominator would comprise one or more distinct irreducible quadratic factors of the form ax squared plus bx plus c, such as the quantity x squared plus 6x plus 3. And finally, in case 4, the denominator would comprise one or more repeated irreducible quadratic factors of the form ax squared plus bx plus c to the m power, where m is greater than or equal to 2, such as the quantity x squared plus x plus 8 squared. Note that each case specifically refers only to the denominator of the expression. Let's try an example. We will find the partial fraction decomposition of a rational expression with a numerator of x to the 5th power plus x to the 4th power minus 2x cubed minus 7x squared plus 25x minus 25, and a denominator of x squared times the quantity x squared minus 5 squared. This expression has a denominator that comprises repeated linear factors in the form of x times x. Additionally, the denominator also comprises repeated irreducible quadratic factors in the form of the quantity x squared minus 5 times the quantity x squared minus 5. Thus, we need to use case 2 and case 4 to find the partial fraction decomposition. Case 2 states that any linear factor repeated m times will result in the sum of m partial fractions where a and b are constants to be determined later. So we have a over ax plus b over ax plus b squared. Case 4 states that any irreducible quadratic factors repeated m times will result in the sum of m partial fractions where cx plus d and ex plus f contain constants c, d, e, and f to be determined later. So, we add cx plus d over ax squared plus bx plus c plus ex plus f over ax squared plus bx plus c all squared to the first part of our expression. Note that lowercase a, b, and c are different in each denominator and are just placeholders. Now, we can substitute the appropriate denominators into each term in our expression. This gives us a over x plus b over x squared plus cx plus d over x squared minus 5 plus ex plus f over x squared minus 5 squared. We have now written our expression as a sum of rational expressions. However, we are not finished until we determine the values for a, b, c, d, e, and f. Let's solve for these now. Start by multiplying both sides of the equation by the lowest common denominator of x squared times the quantity x squared minus 5 squared. When we multiply both sides of the equation by the lowest common denominator, it cancels the denominator on the left side of the equation. However, we need to be cautious on the right side of the equation, as only certain factors are canceled as we distribute the lowest common denominator. And so, the equation is now x to the 5th power plus x to the 4th power minus 2x cubed minus 7x squared plus 25x minus 25 equals ax times the quantity x squared minus 5 squared plus b times the quantity x squared minus 5 squared plus the quantity cx plus d times x squared times the quantity x squared minus 5 plus the quantity ex plus f times x squared. Distribute on the right side of the equation to clear the parentheses. Thus, the right side of the equation simplifies to ax to the fifth power minus 10ax cubed plus 25ax plus bx to the fourth power minus 10bx squared plus 25b plus cx to the fifth power minus 5cx cubed plus dx to the fourth power minus 5dx squared plus ex cubed plus fx squared. Rewrite the right side of the equation to group terms with like exponents together and go in descending order. Now let's factor what we can. So, factoring the right side of the equation yields the quantity a plus c times x to the fifth power plus the quantity b plus d times x to the fourth power plus the quantity negative 10a minus 5c plus e times x cubed plus the quantity negative 10b minus 5d plus f times x squared plus 25ax plus 25b. Comparing the polynomials on both sides of the equation helps us draw the conclusion about the coefficients of these terms. For example, the quantity a plus c times x to the fifth power on the right side of the equation corresponds to x to the fifth power on the left side of the equation. So, a plus c equals 1. We can apply this pattern for all terms and generate a system of 6 equations as a result. So, a plus c equals 1, b plus d equals 1, negative 10a minus 5c plus e equals negative 2, negative 10b minus 5d plus f equals negative 7, 25a equals 25, and 25b equals negative 25. Solving this system of equations gives us integer solutions of a equals 1, b equals negative 1, c equals 0, d equals 2, e equals 8, and f equals negative 7. Now that we know the values of our constants a, b, c, d, e, and f, we can substitute them into the right side of the equation. Thus, the partial fraction decomposition of the given rational expression is 1 over x minus 1 over x squared plus 2 over the quantity x squared minus 5 plus the quantity 8x minus 7 over the quantity x squared minus 5 squared. We can prove that our answer is correct by adding these rational expressions together to get the original rational expression.